My name is Jack Gallant. I'm a professor of psychology and neuroscience here at UC Berkeley, and my lab works on vision. That's our main focus is on the visual system. And vision's a really important thing to work on because humans are very visual animals. And when humans have damage to their visual system, they're really incapacitated. And natural vision is a lot like watching a movie. So essentially, we were trying to build a model that describes how your brain responds to movies. So if the external world is a certain kind of movie, we want to be able to build a dictionary that will allow us to accurately predict what the brain activity would be that would be evoked by that movie. And then given some brain activity, we want to be able to reconstruct the movie that you saw. So on the left here we have a movie that we showed a subject in the magnet. And on the right we have a brain. And you can see the brain activity is painted here on the side of the brain, but the brain's kind of crunched up in the skull, so it's hard to visualize. So we kind of inflate it, and then we flatten it out, and we can see a flat map of the visual cortex and the rest of the brain as the person watches the movie. The problem here for us is to translate between these movies that occur and this pattern of brain activity that occurs. And in the study we talked about in our paper, we just modeled this very back part of the brain, the early visual system, primary visual cortex. And that part of the brain responds to the little local features in the movie, little edges and colors and pieces of motion and texture. But this part of the brain doesn't know anything about what the objects are in the movie. First, we put people in the magnet for several hours, and we show them movies, and we build a model of their brain. And then in the second part, we put them back in the magnet, we show them new movies, and we measure their brain activity, and we decode their brain activity in order to reconstruct the movie. So on the left here is the movie we actually showed people, and on the right is our reconstruction. When the movie that we showed has a fairly common object like a person, our reconstructions are actually fairly accurate. But when the movie that we showed is something rarer, as you'll see in a second, like this abstract thing, then our reconstructions are coarser. Not really so much over here, I guess. I think you'll be able to use this kind of technology for communicating with people who can't communicate, like locked-in patients or people with neurological diseases. I think you could maybe use this in some forms of psychotherapy or dream analysis. I think there's a lot of potential clinical applications for this. When this model worked, we were very happy because it was really quite surprising that it would work at all. We're only taking snapshots of the brain every 1 or 2 seconds, and our reconstructions of movies happen at the movie rate. So that's much faster, and there's no reason one would think that this would work. And in fact, most of our colleagues just told us this would never work. So it was pretty surprising and satisfying when it actually worked.